Welcome everyone! Today's art and science video will be about the fabulous Lichtenberg figures. Before we start, we need to warn you that this experiment can be dangerous. We'll be using high voltage up to 1000 volt, which can be deadly. So if you're not a professional, don't try this at home. But first of all, what are Lichtenberg's figures? They are root-like patterns that can be observed when we try to pass a current in materials that don't conduct electricity, like wood, air, or plastics. Pretty much everybody has already seen those patterns, because in air, they are actually lightning bolts. For today's experiment, we'll try to produce those patterns in wood. Why wood? Because it's a non-conductive material like air. But how do these patterns are formed? To understand it, first we need to review our notions of electric circuits. Let's take, for example, a battery that is connected to a closed circuit. In this circuit, the electrons will flow directly from one end to another. That's why it's called direct current. However, there is another type of current that exists. It's called alternative current. Everyone should be familiar with it because it's the one we have at home. With this type of current, the electrons go back and forth in the wire. To better understand, we need to draw their voltage across time on a graph. First, if we draw direct current voltage, we need to draw a flat line. However, with alternative current, the voltage varies across time in the same way. In this experiment, we'll use alternative current. You'll get later why. In order to understand how Lichtenberg's figures are made, we need to better understand how electricity behaves in a circuit. In general, we can say that electricity is lazy. It will favor the path of less resistance. In our example, electricity will go through more the path on the left because it has a less resistance than the path on the right. But what happens when you try to pass a current in a non-conductive material at a really high voltage, like 1000 volts? Let's try it. We'll use wood as a non-conductive material and a microwave transformer. Ta-da! Why use a microwave? Because in it, there's a really powerful transformer that we need for the experiment. The transformer is located right here. Here's the circuit we'll use for this experiment. Here's the transformer. The current will go from the wall through the wire in the transformer. The voltage will be increased to 1000 volts. Then it will go through the wires and try to get through the wood from one wire to the other. However, wood is a really poor conductor, so we need to add something to help it conduct electricity a little bit better. To do that, we'll use a mix of water and baking soda. When baking soda is put in water, it produces ions, which will help electricity go through the wood. So we only need to put a little bit of that solution on our piece of wood to make sure that electricity will find a way to go through it. Let's try it now. Ta-da! What we see here is the electricity going through the wood. But why does it burn? It's because when electricity goes through a material that has a high resistance, it produces a lot of heat, which ignites the wood. When the wood has stopped burning, don't forget to close the current. It's still dangerous. Before we can observe our Lichtenberg figure, we need to clean the piece of wood. But what happened there? Let's go back to the drawing board. So in our setup, we had our piece of wood, our electric source, and our ions that were there to help current go through the wood. Now, the electricity tries to go through the wood, but there is no clear path of less resistance, so it tries many paths at the same time. The alternative current causes a back and forth motion of electrons at both ends of the wood piece. Some regions of the patterns are darker than others. That's because more electricity flowed through there, generating at the same time more heat. Those are the reasons why we have those beautiful Lichtenberg patterns. We would like to thank you all for watching.